ESIG Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we canceled the physical meeting in Tucson due to the coronavirus situation, and we decided to proceed with a shortened online version. We started the series of 12 webinars in mid-March, and we're running through early May, approximately twice a week. You can find the full schedule at the ESIG website under the Events tab. Recognizing the limitations of a webinar with typically more than 100 people on the line, we'll have individual presentations of 10 minutes, followed by a discussion period at the end of the session, moderated by the session chair. The lines will be muted, so we will ask you to use the Q&A box in the lower right-hand corner of your screen. Today, we'll be hosting Session 9, Operations Planning for Storage and Hybrid Power Plants, chaired by Tom Acker. Tom is a professor of mechanical engineering at Northern Arizona University, where he heads the Clean Energy Research Group. His current research interests lie broadly in renewable energy integration, wind assessment, water energy projects, and Native American applications of renewable energy. Tom has been involved with ESIG for many years and is a good friend. Tom, we appreciate having you here, and I'll now turn it over to you.
Thank you, Charlie. I'd like to welcome everyone to Session 9 on Operations Planning for Storage and Hybrid Power Plants. Today we have a timely session related to hybrid power plants. With the large increase in clean energy resources on our electric systems, particularly wind and solar, we've experienced a need for increased flexibility in our power systems and the markets in which they operate. Hybrid power plants are new entries to the power system within the last few years and are typically facilities with co-located generation and storage that can inject and or withdraw energy. Today's session will consider hybrid power systems, power plants, and storage from several perspectives, and I think you will find the presentations very interesting. Our first speaker is Will Gorman. He is a graduate student researcher in the Electricity Markets and Policy Department at Lawrence Berkeley National Lab, where he focuses on the integration of variable generation into the electric power system and the economics of distributed energy resources. Previously, Will worked with the utilities practice at the Brattle Group, an economic consulting firm where he focused on wholesale electricity market and retail rate design. He also has held positions with Boston University's Institute for Sustainable Energy, as well as UT Austin's Weber Energy Group. Will has his master's in energy and resources from the University of California, Berkeley, and is currently working towards his PhD in the same department. Will's title for his talk today is The Rise of a Hybrid Power Plant, and I'll hand it over to Will.
Great. Thanks, Tom, for that kind introduction. And thank you, Charlie, for inviting me to participate on this panel today. I'm very excited to kick off this timely topic on hybridization and storage. And am honored to be included with the rest of the panelists who are on today. We've got a great lineup. I am sad that we weren't able to meet in person to have this conversation with you all, both on the phone and then on the panel, but look forward to having future conversations, hopefully in person at ESIG workshops later down the road. So without further ado, let's kick it off. Let's talk about the rise of the hybrid power plant. So in the first few slides, I want to kind of introduce the topic, provide at least my definition of what I think about when thinking about a hybrid power plant, and hopefully set the stage for the remainder of the conversations that will be happening on the panel. So, as Tom mentioned, there's no surprise to this ESIG group that integrating kind of high penetrations, high levels of variable renewable energy will require strategies that enhance grid system flexibility. And storage has become a very popular topic to provide this enhanced flexibility, partly due to the declining cost of batteries. And I think the conventional wisdom, over the last 10 years, when thinking about system operators and balancing authorities, was that these operators would take advantage of a geographically dispersed technology set and asset set and operate the system in a way that controlled, optimized the kind of dispatch of these disparate technologies to ensure reliability. But what we've been seeing, and partly why we're having this panel, is that developers have shown an increasing interest in co-locating generation technologies with batteries at the point of interconnection, rather than siting them separately. And so that's somewhat of a different perspective and a way to think about how technologies should be deployed on the system, where balancing is done kind of closer to the point of generation rather than on the system as a whole. So that's something to think about when thinking about this hybridization. And these topics and discussions are timely because wholesale market regulators are having discussions right now to set up the rules to integrate these new types of hybrid configurations. And so this is happening, CAISO, we've shown a number of different groups in the ISOs that are thinking through these rules, but also at FERC. And so there's a need, for information on what are the advantages and disadvantages of these hybridization and how will they ultimately participate in the markets because they are a new type of resource with different capabilities than maybe we have seen before. And so, so I've spoken, about hybrids generally should be a little bit more specific on at least how I think about what this term means. And so me, as well as collaborators I have up at the lab, really think about hybrid as applied to any project that combines multiple energy generation, storage, even load control technologies, both physically co-located and virtually linked. But this kind of term, many people can disagree, reasonable people can disagree on what this definition should be, and I'm sure we'll hear some more perspectives as we go throughout the remainder of this webinar. But in the remainder of my particular presentation, I will kind of move away from that broad definition towards a very specific class of hybrid projects, which are co-located generators and batteries. And the reason that is what I'll focus on in the remainder of this presentation, and what we've been focused on mainly with our research up at the National Lab, is that battery plus generator hybrids really have the highest commercial interest, kind of out of all of the technology sets, at least in the near term. And so while that does not kind of dissuade thinking about the broader space of hybridization, it's important to kind of hone in and think about why these technologies, these particular type of hybrids are being developed. And so to that end, we've thought through qualitatively, at least, some of the pros and cons of hybridization against these battery generator hybridizations versus developing standalone projects. And so I think if you talk to any developer or a lot of people in the industry, a big cost advantage for deploying these projects is the investment tax credit. And so this is the fact that if you deploy storage with a renewable energy asset and you charge that battery at least 75% of its energy from that storage device, you qualify for roughly a 30% discount on that storage device. So that's a huge incentive. But there are also other cost synergies mainly involved with construction that might be important when considering the incentives to develop these hybrid projects. But there's also this notion of market value synergies. And the idea here is that potentially the whole, so the hybridization project, the battery plus storage, that whole is greater than the sum of its parts. I think the idea here, which is one that we're exploring a little bit in future research, is that you have energy constrained resources like batteries, storage, and then you have these variable renewable resources that separately have different ways that they've been integrated into the markets that deal with those kind of shortcomings. And then the question really is, by combining those two things into one asset, do you potentially get some synergies that lead to market value benefits? And so that's a potential pro to think about. But there are also cons that we've outlined, and these are mainly related to operational and siting considerations. So the siting being probably the biggest constraint, and I mentioned a few slides earlier about this idea of the geographically dispersed grid that is balanced, and locating each asset in its optimal place for the system value. But by hybridizing, you're co-locating two resources that potentially would have been cited separately if you thought about them differently. And so that's a constraint that you want to think about when making this choice of hybridization. So to move on, start to talk about some data, start to share what this large commercial interest is. So we looked at the 7 ISO and RTO queues, interconnection queues across the US, and of the 240 gigawatts of solar PV that exists in these queues, 25% of it is being paired with a battery. Now this drops to 4.3% for wind and even lower for natural gas, but in total, it's about 70 gigawatts of hybrid generator capacity in these queues, which roughly represent maybe 50% of the peak load in the United States. So a really big investment and interest in these technologies. And the graph on this to the right, this blue graph, kind of shows how this interest is very recent. So the majority of these projects have entered the queues in 2019. And so showing that this is really within the last few years that these projects have been proposed. Diving a little deeper into the regional story, California is by far the leading market. In the 2019 applications, 96% of PV and 75% of wind is paired with batteries. So that's a huge amount. We do see interest. You can see in the table, the screen table on the right, interest in hybridization in other queues, especially PV hybrids, but California really is leading the way. And I'll show in a few slides how wholesale pricing patterns might be one of the explanations for this. Another big driver of these projects is the costs. So this chart shows levelized PPA prices for PV battery projects over the last 5 years, and it shows that there's been a halving of these PPA prices. So we've seen the dramatic decrease of PV prices. That started to happen with batteries too, and you see that in these hybrid projects, making them cost competitive. So the final kind of technical thing I want to share is this notion of pricing patterns potentially driving which areas of the country are seeing interest in these technologies earlier on. And so we ran a pretty simple optimization algorithm to dispatch a storage device in both the California market and the Texas market for wind and PV. And we found that in California, there would have been much more value added than in Texas, considering energy and capacity prices from 2016 to 2018. So we found maybe a $30 increase when you add a battery to a PV or wind plant, compared to a $5 to $10 increase in Texas. And that's really thinking about the pricing that has happened because of the high penetration of solar in California. And this is something that we want to kind of expand further with research looking at other regions. And it's interesting to compare this to the PPAs on the prior slide, where we found storage adders of around $10 a megawatt hour, and that can be compared to these $30 in California and $5 in Texas. So I'm out of time. It was a whirlwind tour of the commercial interest. Just to conclude, the main points of this presentation were to communicate there's high commercial interest in these generator battery hybrids, and co-locating these batteries with renewables could offer significant value. So with that, look forward to questions, and if your question doesn't get answered, please reach out. I'd love to engage on the research. Thank you very much.
Thank you very much, Will. We have 7 speakers in today's session, so what we're electing to do is go through each of the 7 speakers and hold all the Q&A until the end. We'll be looking in the Q&A box here to see your questions that we may be able to get to at the end. When you put in your questions in the Q&A box, since we're going to be traveling through all the speakers here, would you please put the name of the speaker for which you intend the question? That would be helpful. So with that, we'll move to our next speaker. Our next speaker is Mark Ahlstrom. He is the Vice President of Renewable Energy Policy for NextEra Energy Resources, and he's President of the Energy Systems Integration Group. Mark is actively involved with grid operators, NERC, FERC, DOE, industry groups, and many activities to support the economic and reliable use of very high levels of clean energy. Mark's talk today is Hybrid Resources, the role and value of hybrid resources in the not-so-distant future. Mark, take it away.
Thank you, Tom. Yeah, I just wanted to make a few comments here. As some of you know, I've been talking about hybrids for the last year pretty much. And so if you've been to some ESIG meetings, you've probably heard me preach some of this, because I've become a big believer in some of the real advantages of this to the system and to the development community as well. So as was mentioned here, I'm focusing on a particular definition of hybrid resources, where it's a combination of technologies that are controlled by the owner-operator of that power plant behind the point of interconnection and offered to the grid as a single resource. In other words, it becomes a single power plant that's even different than its components. Now, it is certainly possible to put multiple resources behind the same point of interconnection and operate them as multiple resources in the market and the energy management sense. I would refer to those as co-located, which is also the language that the California ISO has used to distinguish the two types of participation. So a quick definition, you know, I would also agree with Will that, I mean, what we're talking about here is actually the simplest form of a virtual power plant, right? It's basically two resources in most cases that are sharing a physical location and a single, you know, physical connection to the grid. There's two common designs that come up. The first that everybody thinks about is the AC coupled I'm showing on the left here. The idea here is these are just kind of, you got a PV plant, you got a battery plant, and you just share an interconnection. The main reason you're going to do this is because you might not need the full capacity of interconnection all the time. So it might be like a 100 megawatt PV plant, and you want to add maybe 60 megawatts of batteries there, right? But you don't want to pay for 160 megawatts of interconnection because that gets to be expensive, so you're going to share that. Now that seems simpler, and I would agree with Will that in this case, you do end up with some operational flexibility problems that I think actually make this design, you know, less interesting and less desirable in many cases. For example, if you're going to separately offer both of these to the market, but they're constrained at the point of interconnection to 100 megawatts in total, well then how do you deal with the simultaneous dispatch of those in the market sense? Because that's a constraint, but you don't want to set price inside your own power plant and be competing with each other to lower your price of your PV and storage value, right? So it can't be treated like a normal constraint in the system. Also, and a point I'll dwell on a little bit later, is on what California calls resource adequacy, or what is commonly called capacity value in other places. You know, if you're getting a capacity value like for the batteries of a certain amount, does that mean you have to retain that capability reserved for the batteries for deliverability of that all the time at your point of interconnection, which also kind of throws away a lot of the value of even thinking about a hybrid, right? Why would I save 60 megawatts out of the interconnection for the battery to get capacity value and I get 100 megawatts of PV there that I can't deliver most? And then, of course, you have to be able to charge between, you know, from the PV to the batteries in various ways, which also gets complicated. That's why I've been a huge proponent of the DC coupled design on the right. The idea here is you actually put the batteries and the PV behind the same inverters, right? So conceptually, it's a single bidirectional inverter. There is a DC to DC converter just because typically batteries and PV panels like to operate at different voltages, but from a market point of view, that disappears as well, right? It's these DC coupled resources behind a single 100 megawatt inverter, and that becomes a single resource, which no longer looks really like PV or battery. It's now something new, right? I would point out too that in my view that inverter should always be a bidirectional inverter. There's not a significant cost differential really between a bidirectional unidirectional inverter like you would use for a standalone PV plant. In fact, I would go so far as to say that you're doing a disservice to the grid if you don't use a bidirectional inverter there. And we'll talk briefly about why people might be tempted not to because of the investment tax credit, but I think that's not really a valid reason. So the reason you really love to do the DC is because you can put a lot of additional PV capacity and battery capacity behind that interconnection, sharing the inverters, right? That's the whole idea. If I'm building a standalone PV plant, because panels are cheap, I might already oversize and have 130 megawatts of PV panels for 100 megawatt solar plant standalone. But if I got a battery there, I'm probably going to put in 180, 200 megawatts of PV panels, knowing that I'm going to clip a lot of that during the afternoon, but that I can then charge the battery with that and then use that battery capability for other services. Not just energy, I would point out, but ancillary services, reserves, you name it. You can do everything. So that's the advantage here, is that the whole idea of a hybrid is you're going to have a lot of additional capacity back there that's going to be used for delivering a whole range of very flexible services to the system. So what are some of the key benefits, just briefly here? I'm really proposing, to be blunt about it, that once you become a hybrid in this way, you're probably willing to give up special treatment for being a variable resource. Now, having intra-hour schedule adjustments might make sense for all flexible resources. There's a lot of logic to that, to do that in a technology-neutral way. But you might not need the dispatchable intermittent type rules. You also don't need the system operator to control your battery state of charge. I think FERC Order 841 to get batteries into the market as standalone is a necessary step. The reality is it's actually a real pain for the system operator to have to manage the individual state of charge on what's going to be thousands and thousands of batteries out on their system. So I'm actually arguing that should be internalized, and that should be you own the power plant, run the power plant, right? Also, we've seen some great studies about how wind and solar plants can be a very flexible source of ancillary reliability services. They can provide reserves and regulation very, very quickly, very well, respond to contingencies and so forth. For some of those, like those reserves, to do it, though, you've got to retain headroom. You've got to not be delivering energy so you have some headroom to respond, which is very difficult for a PV plant, given that you're giving up your energy sales to do that. With a hybrid, especially the DC coupled, you don't have to. You're trying to use all of the clean electrons that come off the renewable source all the time. And if you need headroom, you just charge the battery faster and create headroom at the point of interconnection on a net basis, right? So the idea is you can do all these services without spilling clean electrons. I mentioned too that a lot of people, of course, if you charge the battery at least 75% of the energy over the year for the first 5 years of the project, that battery investment can qualify for the solar investment tax credit. So everybody says, well, I want to charge it all the time, right? Especially for that first 5 years anyway. I want to be able to clearly show 100% of the time I'm charging so I get the full investment tax credit. Well, that's not what the rule is. The rule is 75%. At 25% of the energy over the year is actually a lot of energy. So it really comes down to an economic choice, right? If the services you can provide by emulating this fantastically flexible resource, with your storage, your energy, your electronics, and your software, you can emulate any kind of electrical machine you want. You can do every sort of service that any other power plant could do. But is the value of doing that sufficient to force you to charge the battery part of the time in order to make sure you can provide those other services? That's a market issue. That's is it an economic choice? And finally, I would point out that I'm actually proposing that you don't even need a new market participation model for this type of hybrid. You pretend I'm a combined cycle gas plant and allow me to just turn off in the master data file the parameters, because I'm like a gas plant, only I have no startup costs, I have no startup time, I have no minimum gen level, I can ramp all the way down to 0 or even negative. So I'm like the most flexible gas plant you could ever dream of, right? And what you end up with is what they call fully convex one-part offers if you're a market design wonk, which is exactly what you want in a market. That's how essentially all other markets operate, with very simple, energy supply curves, without these non-convexities, they call them, like your startup cost and your no load fee, right? So that's the idea: is can we make this simpler rather than more complicated? So my last slide here, just a couple of discussion points keep coming up and have been kind of nagging at me, so I wanted to just mention a few. First of all, as well mentioned, we all agree, I think, we're going to need more flexibility in real time as we go in the future to keep everything balanced, what we used to call system security, really, right? But, this is what, as long as you can balance supply and demand all the time in real time, you're going to be a reliable grid. I would argue that hybrids are a great source of this type of flexibility in energy services and can evolve very quickly to do it even better. So if you want a resource that's going to allow you to do real-time balancing, this is fantastic. What about these interdependencies? Are hybrids really less flexible than something else? And who should be responsible for that? I mean, my point is that if the owner-operator of the hybrid plant is willing to internalize this and make this offer in a very simple sort of way with the market, that their performance should be, measured on a performance basis, right? Penalties for failure to perform, bonuses for superior performance for exactly the services that the system actually needs. This would allow us to simplify the market software and the operational software, not to make it more complicated, right? The reality is, I'm not asking the ISO RTO to go inside of my plant and optimize things for me. I think the owner-operated plant is the one that has all the knowledge to understand all the details in terms of battery degradation and use and how those should be done. And to the extent they're willing to internalize that and make simpler offers and hedge their risk in other ways using better forecasts and so forth, they should be not only allowed to do it, but they should be encouraged to do it. And they should be allowed to offer all types of services, not just energy to the grid, that they can show that they can provide. Now, what about, though, you say, well, yeah, but you're still energy limited. You only got so much battery storage there. You can't sustain your duration for, 20 hours. Agreed. But I think we've kind of lumped all this together in what we call, capacity value or resource adequacy, because there's going to be a longer-term issue. Okay, what about the 4 days once a year where California doesn't have any sunshine and most of the resources are solar? That starts to feel very different from expecting that these resource adequacy resources are going to be producing at peak, and it's the capacity planning margin that gives me this reliability. I think it's really bifurcating here. We've conflated these two concepts, but for real-time balancing, you want these highly flexible resources. For long duration, I agree. Once a year or so, you're going to need to have these long duration, but those can be less flexible resources. Those could be gas plants, those could be imports, those could be something else. It's almost like it's a contingency because it's so rare, but it happens really, really slowly over hours or days, right? And in fact, you might not want those longer duration resources like a gas plant to be running during peak because you want to have your most flexible resources there to deal with the balancing because of the need for flexibility and ramping. So I would argue that you might actually end up with a different type of adequacy, which is stuff you need to recharge your flexible hybrids and storage. And maybe you want that at 4 a.m. more than you do at peak, right? So it's a different thing. I don't even know what we would call it, but it starts looking more like a contingency, only a slow event. So with that, to start discussion, I look forward to the questions and Q&A. Thank you.
Thank you very much, Mark. Our next presentation will be from Thomas Mosier. Thomas is the Energy Systems Group Lead at Idaho National Laboratory. The group performs research on power system stability, resilience, and integration across a wide range of technologies and use cases. Thomas's background is in hydropower research, and he serves as the research area lead for technology innovation within the DOE HydroWires initiative. The title of his talk is Hydro Plus Storage, Flexibility to Enhance Services and Enable New Capabilities. Thomas?
Great, thank you, Tom. Yeah, so the context of my talk is that the hybrids discussion is permeating across industry and has been on the minds of hydropower owners and operators for the last year plus. We've been doing this project funded by DOE's Water Power Technology Office for several years now. It's a joint partnership between Idaho National Laboratory, Argonne, and NREL. So I'll be talking about enhancing services and enabling new capabilities in the context of a couple of examples, case studies that we've done. But first, so the context, of course, is that the grid is requiring and therefore valuing flexibility higher. And so we want to enable the hydropower industry to increase their flexibility through the use of energy storage devices or virtual reservoirs. So the project has taken a ground-up approach. In partnership with Siemens, developed a control architecture that is agnostic to the type of energy storage device or the type of hydropower plant. An initial starting point for the project was looking at the run-of-river fleet, which, depending on your definition of run-of-river, has either no flexibility or limited flexibility. And so in a market context where flexibility is being valued higher, of course, is an important starting point to help them out and better participate in the evolving market. But even the dispatchable hydropower fleet is providing an excellent resource to balance the grid, in particular in places like the Pacific Northwest, where there's an abundance of hydropower. But I just want to make the point that hydropower assets are critical infrastructure for a variety of societal purposes, only one of which is the power system. So we utilize reservoirs for flood control in the winter and spring. We use them for water supply in the summer and early fall, and we all enjoy recreating on our waterways and our lakes and reservoirs. And of course, needs to operate them in a way that minimizes impacts on the environment. And so these are all overlapping objectives with respect to operations, and therefore, there's a role for hybridization to play across the fleet, even in our reservoir-based resources, to provide certain values and increase the flexibility. And so in discussions with industry, there are lots of different value streams and use cases on their minds, ranging from increased market participation, so ancillary services, to how do we reduce the wear and tear on these big synchronous machines as they're being called upon for more ramping and more starts and stops, to grid modernization paradigms. So how do we use integration of energy storage to produce new capabilities in certain segments of the existing hydropower fleet? And in the remainder of my slides, I'm going to focus on two examples, a case study and a preparation for a field demonstration, work that we've done with Idaho Falls Power to demonstrate some of the use cases for hybridization. So for those of you who don't know, Idaho National Laboratory is located in Idaho Falls, and Idaho Falls has a municipal hydropower utility that owns and operates 4 main run-of-river generation assets on the Upper Snake River, as well as the distribution and sub-transmission system that's connected into Rocky Mountain Power. So under typical operating conditions, Idaho Falls Power provides about 30% of the electricity to the community annually, but does not do any of the balancing that's done by Rocky Mountain Power. But using this as a hypothetical case study, since we have good, readily available data on the generation, and the run-of-river plants are representative of other parts of the U.S., we did a case study looking at if these plants were located in CAISO and able to participate both in the energy and ancillary services markets, what would the revenue be under the current run-of-river only scenario versus hybridization with either batteries or flywheels, which would enable them to participate in ancillary services and perform energy arbitrage. And so using the Cheers market participation model developed by Argonne, we found that mainly through frequency regulation and energy arbitrage, that hybridization was able to boost revenue in this case study by between 12 and 16%, where the majority of that variability in revenue came from the market assumptions that we used. So there's definitely the potential for hybridization, and of course the revenue depends on the generation profile and the market context and the energy storage configuration that you're looking at. But we've seen other parts of the U.S. too. American Electric Power is an example of a private sector entity who has invested in batteries at two of their existing hydropower plants and has seen useful revenue increases for their context selling into PJM. In addition to boosting revenue, we have been working with Idaho Falls Power on looking at enabling new capabilities through hybridization of their run-of-river assets. And so Idaho Falls is in eastern Idaho. It's a regionally important hub in terms of medical services and other critical services. As well, it gets quite cold in Idaho Falls in the winter, as some of you may know, and there have been a couple instances where there were transmission outages when the low temperatures were close to 0 degrees Fahrenheit, and the outages lasted, in one instance, multiple days. So it's a public health risk. And so Idaho Falls Power has been relatively forward-looking in terms of thinking about how could they island their system and increase the reliability and resilience to their customers and to the region as a whole, using both their own generation assets and potentially the increasing wind projects that are at the same point of interconnection, for example, the Goshen Wind Project. And so the team has been working with them to help them think about and provide solutions to enable them to do a distributed black start and islanding of their grid system. A question that people may have is, well, what's new here? Because hydropower assets at the transmission level are critical for black starts, but there's fundamentally a difference in the scale and corresponding capabilities of a lot of the smaller hydropower assets that are tied to the distribution or subtransmission levels. And so Idaho Falls Power, the bulk of their generators are bold-style variable pitch Kaplan units that are designed for optimal efficiency at low heads, but they're not designed for optimal stability. So the question is, can we use improved controls and hybridization in order to increase the stability and enable these new capabilities? So we were planning to do a field demonstration with them to demonstrate this next week. Unfortunately, due to the obvious COVID-19 situation and travel restrictions, that's being postponed. But we've still done simulations and hardware-in-the-loop testing to support the concept. And so what this graph here is showing a set of simulations. The blue and orange lines are the hydro units only with different control schemes in response to step increases in load that would correspond to the black start procedure. And the gray, yellow, and green lines correspond to energy storage systems that could be hybridized with the existing plants and control options. And what we see is that through the combination of hydro controls and hybridization that we are confident that we can increase the stability sufficiently to enable a distributed black start and islanded operation of the grid. So we look forward to being able to prove that when the field demonstration does happen. And so as kind of my final wrap up here, where the team is going from this point is continuing to work with industry to package these different value propositions and think about how to stack them in industry relevant context. So it could be some combination of increased revenue, decreased operations and maintenance, and potentially some of these new resilience capabilities that we'll be working with industry to explore and develop tools to help them accelerate the development in consideration of And so with that, I'm happy to have any discussion either in the question section, or please feel free to send me an email at thomas.mosier@inl.gov. And I want to thank the other lab contributors and co-PIs and our private industry partners and DOE's Water Power Technology Office. Thank you.
Thank you, Thomas. Our next speaker will be Andrew Mills. Andrew is a research scientist in the Electricity Markets and Policy Group at Lawrence Berkeley National Laboratory. Andrew conducts research on the integration of variable generations in electric power system, evaluating the cost, benefits, and institutional needs of renewable energy transmission and other supporting infrastructure. Andrew has a PhD in Energy and Resources from UC Berkeley and a BS in Mechanical Engineering from the Illinois Institute of Technology. His talk is entitled Solar Plus Storage for Resource Adequacy and Ramp Control. Andrew.
All right. Well, good morning, and it's an honor to be a part of the panel today. I'll provide a brief summary of some of our research on solar and storage plants that came out of a consortium of utilities and researchers in Florida that was funded by the DOE Solar Energy Technologies Office. And much of the work that's presented here today was conducted in collaboration with Pia Rodriguez while she was at LBNL. The key points from my remarks are that we've validated a simple method for estimating the resource adequacy contribution of solar and storage plants. This capacity contribution depends on the utility load profile and the configuration of that solar and storage. We also have seen that storage can help small balancing authorities manage ramps from solar, though there are costs that increase with the stringency of these ramp rate limits. As a consequence, it might be best to try to take advantage of any geographic diversity before trying to manage these ramps with a battery. Our objective in this research was to develop a method to quickly and easily estimate the resource adequacy contribution of solar and storage, such that we could survey a wide variety of different configurations. In some of the previous Spring 2020 ESIG webinars, we've heard about the detailed methods for calculating the effective load carrying capability of resources using these probabilistic loss of load probability models. Here we're going to be calling the contribution of a resource towards meeting these resource adequacy requirements the capacity credit. We approximate this capacity credit by focusing on reducing the load during the top 100 peak load hours. In effect, we're assuming that the risk of insufficient generation is concentrated in these peak hours. More specifically, we calculate the capacity credit as the average difference between the load and the net load in the top 100 hours, which is highlighted here on the right in this green shaded area. Our research contribution was to find a way to dispatch storage to maximize this capacity credit defined in this way. And the algorithm maximizes this capacity credit by minimizing this orange area under the curve here. The method is a fast linear program, and it's easy to implement with open source software. But more importantly, the results of the calculation also yield insights that match with a more detailed loss of load probability-based model. So here we're comparing the capacity credit from our approximation to a benchmark that's based on the effective load carrying capability for different storage durations using data that's representing 3 of the Florida utility partners. We have FMPP, which is the Florida Municipal Power Pool, JEA, which is a municipal utility for Jacksonville, and then the city of Tallahassee. We move on the chart from left to right. It shows that increasing the storage duration also increases the capacity credit for both the approximation and for the benchmark. The capacity credit of solar alone, which is here on the far right, is similar in magnitude between the approximation and the probabilistic benchmark. There is one place that this approximation fails to generate quantitatively similar results for the capacity credit, and that was for the city of Tallahassee, these ones that are marked here in red. This small utility has a really large generator relative to its peak demand, which means that for this utility, the risk of not having sufficient generator to meet demand falls well outside of just these top 100 hours. Luckily, not many utilities face this similar issue, so we expect this edge case that we see with the city of Tallahassee to be rare, but it is worth keeping in mind. So in effect, we assume that most utilities will look more like FMPP and JEA in terms of having a lot of smaller generators relative to their peak demand. But today, I'm really excited to also share results from additional validation of the method that was conducted after the release of the original report. Here we again benchmark our approach against the effective load carrying capability, or ELCC, from a detailed probabilistic loss of load probability model. But in this case, we're fortunate to work with a Western US utility that had independently developed their own method for dispatching storage to estimate its capacity credit. So they used the net load from their ELCC study to calculate the capacity credit of 4 hours of storage using our approximation. Both methods here show this declining capacity credit of storage as you increase the deployment within the system. They also show that the capacity credit can increase in systems with higher solar deployments at a system-wide level. So if we now apply our approximation method to evaluate the capacity credit of solar and storage plants, we find some differences among utilities in different configurations. Here we're presenting the capacity credit results for 2 Florida utilities with different load shapes. FMPP on the left peaks in the summer, while JEA on the right has both high winter and summer peaks. If we look at the capacity credit of just solar alone, which you can see from the results when the storage duration is 0, it's higher here for the summer peaking utility than for the utility that peaks in both summer and winter. The capacity credit for storage alone, which is represented by the blue line here, depends on the storage duration. It's not too different, though, between the 2 different utilities. But then for the solar and storage options, we combine a large 100 megawatt battery with a large 100 megawatt PV plant. And we test 3 different options. We have the independent configuration, where the solar and storage have no shared equipment and the storage can charge from the grid. And we have a loosely coupled case where they share an inverter or they have a point of interconnection capacity that's limited to just 100 megawatts. But the storage can still charge from the grid in this case. And then we have the tightly coupled case where they share equipment and the storage can only charge from the solar plant. The key takeaway here is that when the battery is large relative to this PV plant and the duration exceeds 2 hours, coupling the solar and storage in this way can limit the contribution to resource adequacy relative to these independent systems. Again, this is only really an issue, though, when you have this battery that's very large relative to the PV size. We tested the same thing with a 20 megawatt battery and a 100 megawatt PV system, and we didn't see these same issues. Instead, all the capacity credit results were same between these different configurations and the independent configuration. Okay, and then if we restrict the battery to charge just from solar in this tightly coupled case, it only really seems to matter for this utility that has high winter peaks on the right-hand side. Here we saw some events where extended cloudy periods during the winter peaks would lessen the ability to charge storage, and that resulted in a capacity credit of this coupled system that could be even lower than for that standalone storage system. Okay, now I'm going to shift gears and talk a little bit about some of our analysis that we did using storage to provide ramp control for solar. So the Florida utility partners operate very small balancing authorities in which they need to balance their systems to maintain compliance with NERC balancing standards. One of the concerns that was raised was with managing some of these large solar ramps that can be associated with passing clouds. So with them, we examined the feasibility and cost of using storage to limit the ramp rates from solar that are due to these clouds. This chart shows one way that storage could be used to limit the ramp rate from solar to just 5% per minute. Now, note that the battery that's needed for this is very short duration. In this case, it was only a 15-minute duration battery would be needed to meet this 5% per minute ramp limit. We then used this control algorithm and a simple rule of thumb for sizing the battery needed to meet increasingly stringent ramp rates. The more stringent the ramp rates were, that required longer and longer duration batteries to be able to meet that. We then put the charge-discharge pattern from these different batteries into NREL SAM model to estimate how often the battery would need to be replaced within a 25-year period if it was used in this manner. We then spread the cost of this storage over the lifetime of the solar to see what this would do to the overall solar levelized cost of electricity for the solar plant to be able to both have to cover this additional cost of the storage that's needed to meet this ramp rate limit. The results here show that the ramp rate limits with storage could easily increase the costs by more than $10 per megawatt hour of solar. One final note is that we compare the results from 2 different PV plants. We have one small 75 kilowatt plant and one large 12.5 megawatt plant. The larger plant results are shown here in the blue. you see that the larger plant doesn't cycle the battery as much to meet the ramp rate limits, and therefore it has a lower incremental cost relative to that small PV plant. And this suggests that even the smoothing from the within plant geographic diversity can lower the cost of meeting these ramp rate limits. It's therefore important to take advantage of geographic diversity to the extent possible before using the storage to mitigate the solar ramping. So just a quick summary of some of these main points. We saw that the capacity credit of solar varies with the utility, and that the capacity credit of storage depends on the duration of that storage. And we see that large batteries relative to the solar nameplate capacity can limit the capacity credit of coupled solar and storage systems. Batteries can be used to mitigate these solar ramps, but there are costs that have to be considered of this. And increasing the stringency of that ramp rate limit increases the required battery duration, and therefore also increases the cost of meeting those limits. And finally, we saw that mitigating the ramps for small PV systems has higher costs due to these more frequent large cycles. With this research so far, we've really just scratched the surface of this analysis. And so for refining and expanding the research, we recommend looking at more advanced ramp rate control strategies. We looked at a fairly simple one here. We recommend comparing the cost of mitigating ramps with storage to other options that might be available. And then also more detailed investigation of whether extracting multiple services from the same battery can be done at lower cost than these isolated use cases that we presented here. So if you're interested in this, there is a report that we have available on our website that I've shown a link to here. I'm also interested in hearing your feedback in the Q&A today, but do also feel free to reach out. My contact information is listed here on the slide. You can email me at admills@lbl.gov. Thanks.
Thank you, Andrew. We've been talking about hybrid plants to manage reliability and resource adequacy that arise from the high penetrations of renewable energy. Our next speaker will take a decidedly different approach to this problem. Brendan Kirby is a private consultant working with GridLab. He retired from Oak Ridge National Laboratory's Power Systems Research Program. He has 45 years of electric utility experience and has published over 180 papers, articles, book chapters, and reports on ancillary services, wind integration, restructuring, the use of demand response as a bulk system reliability resource, and power system reliability. Brendan's talk is on renewable generation reserve sharing groups. Brendan.
Thank you, Tom. As Tom said, my discussion is not uniquely focusing on hybrid power plants, but hybrid systems could be an excellent resource to supply the resources for renewable generation reserve sharing groups. And this idea of renewable reserve sharing groups, it's coming from a concern that we've seen some utilities increasingly imposing wind and solar variability and uncertainty integration charges. It tends to be from utilities that have got very small penetrations currently, but are looking at having larger and larger penetrations, and so they don't have the experience with wind and solar yet, but nonetheless they are requesting and receiving integration charges. Now, these integration charges can be large. They can be with immediately asking for charges in the range of $1.50 per megawatt hour, $2.50 per megawatt hour, $2.70. But having the analysis showing that their expectation is those charges will go in the next few years up to $10 per megawatt hour on average, and over, nearing $25 a megawatt hour for the incremental. So it's looking at imposing significant charges. So the idea would be that a renewable reserve sharing group might provide a way to reduce or eliminate those charges by the wind or solar plant supplying access to resources to meet the reliability requirements rather than simply paying the integration charge. Okay. Wind and solar impact balancing requirements in kind of two distinct ways: minute-to-minute variability, and then also large but rare drops in wind and solar output. So the minute-to-minute variability, it tends to get mitigated as you get larger and larger amounts, higher and higher penetrations as the fleet grows. And interestingly, the charges we've seen being proposed and sometimes being implemented are based more on these large, rare concerns with those large, rare drops in wind and solar, and it's from production cost modeling, looking at say 10 years of production cost, and seeing what balancing in cost that might impose on the utility. So again, these events are large but rare. They don't qualify as contingency events, as Mark was discussing. They don't qualify because they're too slow. They're ramping events. They take tens of minutes to unfold rather than being instantaneous. But still, the balancing charges are being imposed based on the idea of looking at a 5-minute lack of ramping capability, one event in, say, 10 years, and equivalenting this to a loss of load expectation. Now, for a contingency event, the NERC disturbance control standard requires rebalancing within 15 minutes and then restoring the reserves within 105. If you can't do it, if you can't use contingency reserves because the events don't qualify, then what the utilities sometimes do is then say, well, we're going to increase our minute-to-minute regulation reserves to be able to compensate for these very large, very rare events. That becomes very expensive. So the idea is, again, to come up with a reserve sharing group that may be a cheaper alternative. Now, contingency reserve sharing groups, they're very common, very well established, and they work extremely well. Contingency events are very rare. It's unlikely that generators in different balancing areas will fail simultaneously. So the reserve sharing group of multiple balancing areas only needs to have enough reserves to cover the largest credible contingency within the group. So it greatly reduces the total reserve requirement and everybody saves. Wind and solar drops are similarly rare because they're non-synchronized. So sharing reserves among multiple renewable generators could reduce the cost to compensate for those imbalances to everyone. The reserve sharing group could find the least cost reserve technology available in the area, which could be excess online generation, fast start generation, demand response storage, the flexibility capabilities out of a hybrid plant. Now, it turns out the NERC reliability standards currently recognize 3 types of reserve sharing groups. The contingency reserve sharing groups, they're very common. NERC lists 11. They're very long-lived. They've been around for a very long time, work extremely well. There's also frequency response reserve sharing groups, and currently the Western Frequency Reserve Sharing Group, it's the only currently active one recognized by NERC. NERC also recognizes a regulation reserve sharing groups, and none are currently active. So renewable reserve sharing groups are very similar to contingency reserve sharing groups, operating over a slightly longer time frame. Doesn't appear to be any technical reason that NERC would not allow them to form. So forming a renewable reserve sharing group, existing contingency reserve sharing groups could certainly expand their services they offer. They could cover a longer time frame. They could bring in extra resources. They're already set up to do that kind of thing. If they're unwilling or unable, renewable generators could form their own renewable reserve sharing group. They could obtain the responsive resources through ownership or through contract, and they could then provide that response capability to the local host utility to deal with the wind and solar drops in lieu of paying the wind and solar integration charges. It becomes really important to define the response requirements. That's what's done for contingency reserve sharing groups, and contingency response requirements are very well defined in the NERC standards. Non-contingency balancing requirements are also very well defined in NERC standards. They're both less difficult to respond to and a little more. They're more because the balancing is measured every 5 minutes, or every minute, but requirements are statistical. The balancing requirements are statistical over a year. Rebalancing is required in 30 minutes rather than the 15 minutes for contingency events. But rebalancing is only required if the imbalance is hurting interconnection frequency. So the balancing requirements that NERC imposes for these rare wind and solar events should be less draconian than the contingency reserve requirement, which runs counter to the integration charges we're seeing being proposed. It'd be important to get the host utilities to specify the balancing needs, event frequency, size, duration, that sort of thing, that underlie their renewable integration charges. So in conclusion, the contingency reserve sharing groups have worked extremely well at reducing costs of reliability response to large, infrequent conventional generation failures by spreading that risk over multiple participants. Similar approach could work for wind and solar generators. If the existing reserve sharing groups aren't willing or they're unable to expand their services to cover the rare wind and solar ramping events, obviously with additional resources, it might be possible for wind and solar generator owners to create renewable generation reserve sharing groups as an alternative approach and mitigate or eliminate these high integration charges. Here's contact information. I'm very happy to answer questions at the end, or also feel free to contact me separately. Thanks, Tom.
Thank you very much, Brendan. So for many of these hybrid plants, storage is the key component. Our next two speakers are both from the Department of Energy, and they will be talking specifically about storage. You kind of think of these next two speakers as having a part A and a part B in their talk. Our first one is going to be Alejandro Moreno. He is the director of the Water Power Technologies Office in the Office of Energy Efficiency and Renewable Energy at the Department of Energy. In this role, he manages efforts to develop and commercialize innovative technologies and market solutions for clean domestic power generation from hydropower and marine energy resources across the U.S. Previously, he served in the energy groups of the World Bank and International Finance Corporation, where he designed and led regulatory reform programs to spur investment in clean energy and rural electrification. He holds a bachelor's degree from Stanford University and a master's degree in economics and energy policy from Johns Hopkins University School of Advanced International Studies. He will be talking about the Energy Storage Grand Challenge. Alejandro?
Thanks, Tom, and thanks to Charlie and ESIG for inviting me to the talk today. Apologize to everyone that you cannot see my video. Unfortunately, DOE laptops are not enabled to allow video sharing. As Tom said, my day job is leading the Water Power Technologies Office, which you heard Thomas refer to. We cover all of the department's hydropower and also marine energy research within the Office of Energy Efficiency and Renewable Energy. But more relevant to today, I've been spending a lot of my days, nights, and weekends over the last year as part of a group that's helping to pull together this, what we're calling the Energy Storage Grand Challenge, which is really effectively a DOE-wide strategy on energy storage. And as Tom said, it's not specific to hybrids, but as you hear more and more, I mean, if 96% of new PV is associated to storage in California, and quite a lot of new storage is associated with wind and solar, the two are obviously flip sides of the same coin, or at least very closely related. And so in 10 minutes, I'm not going to be able to go into depth on an entire department-wide strategy, but I will point to where you can get more information on each of the elements I will talk about, including in part on Hsieh, who will speak after me, who will give more information on our technology development efforts. But if there's one message that I really do want to give, it's to talk a little bit about the approach that DOE is taking towards storage, and to give the message that we recognize that not just storage, but that flexibility is an essential component of the grid. The DOE recognizes that the way the grid is evolving makes flexibility in all of its different manifestations a premium, and we recognize that there are many different technology pathways that can meet those different flexibility needs in different scenarios. And that's really what this energy storage grand challenge is trying to develop a research pathway to spur. And so when we first put this together, we got two very clear messages, or three really clear messages, I should say, from our senior management. The first was what I just said, that storage and the grid flexibility it enables are absolutely critical. The second is that DOE needs to do a somewhat better job of coordinating all of the research we're doing related to storage and grid flexibility. And the third is that we need to be comprehensive. We can't just focus on traditional DOE bread and butter, building new widgets, cheaper widgets, but we really need to leverage the full technical and analytical capabilities of the entire department to drive or to maximize the chance that the U.S. can achieve leadership in energy storage technologies and deployment over the next 10 years or so. And so what does that mean for us? It means coordinating in multiple different ways. One is across many different types of technologies, and you'll see we define energy storage quite broadly. Certainly hybrid systems would count as part of that. Part is what we traditionally consider bidirectional storage, batteries, pump storage in my program. But we're also looking at increased flexibility in generation and controllability in loads, chemical and thermal storage as well, both for the grid and for transportation. Recognizing that there are some, while from a technical R&D perspective, there are sometimes overlaps between these and sometimes not. From a use case perspective, in many different scenarios, most of the time you have technologies that can fit in either of these different categories, either competing against each other or working in concert to complement each other. And of course, because DOE is effectively siloed by technology type, this implies bringing together research from many different offices, from the Office of Electricity, where Eric works, from EERE, where I work, and 10 of the 11 different technology offices within EERE have work that's related to this initiative, Office of Science, Technology Transitions, Nuclear and Fossil as well. And then it also means coordinating across different functions that we have. And you'll see on the bottom, we really view the energy storage grand challenge not as a discrete set of opportunities, but a coherent pathway from basic science all the way to commercialization. And what that actually entails for us is 5 specific pillars, which you see here, that are overlapping to an extent, but complementary. And one is technology development. And I'll have one slide on each of these. But one is technology development. One is technology transition or technology transfer. The third is policy and valuation. That's the one that I lead, which is probably particularly relevant to this audience. The fourth is domestic manufacturing, supply chain, end of life, and the fifth is workforce development. So I'll go through quickly one slide on each of these. Eric, again, will talk in much more depth about the first one. If you want more information about any of them, there are many different ways in which you can get that. I'll highlight some at the end, but you can also contact me directly. So for technology development, avoiding stealing Eric's thunder, but just highlighting that because storage embodies, or the storage is embodied in so many different technologies, we're not at a position yet where we're saying, well, DOE is going to pick winners. We try to avoid that in general, and right now it wouldn't make a lot of sense. And so what we are trying to develop is a framework by which we can compare and evaluate different technologies and the ability of different technologies to meet different needs. And so the way this has been designed is by coming up with a series of representative use cases that Eric will talk about, and then distilling from those very specific technology characteristics, technical characteristics, performance requirements that need to be met either in isolation or as part of a portfolio of other technologies to meet those use cases, and then understanding what are some plausible or likely technology pathways. So again, one technology or multiple technologies that will meet those performance requirements and serve those use cases under different scenarios and is part of a cost-effective portfolio. The second here, policy and valuation. This is starting from the premise that there's a lot of information about storage, particularly the way storage performs and the way that operates within the context of the grid that we still don't know. Recognizing that it is not DOE's role to make policy recommendations, but we do have a role in ensuring those who do make policy or regulatory or planning decisions are operating with the best most up-to-date set of information and tools that they can have. And so our role here is working very closely and being informed by each of the different, this is an example of the different types of sort of policy planning, regulatory stakeholders at the bottom here, but having really deep relationships with all of them, leveraging the relationships in many cases we already have to see what are the challenges that are most pressing and how can we improve the data that's out there, for example, data on different performance characteristics under different operating scenarios. How can we improve modeling, planning tools, and then how can we use the data and the tools that we have to have either targeted or broad analytical products that are going to help the wide range of stakeholders make decisions. And this is the type of work that you just heard Andrew talk about, from a very targeted understanding the different drivers of capacity value to potentially very broad things like what you heard Brendan talk about, understanding what are some of the new paradigms that we could conceive and how might they actually play out. All of that analysis would fit within this policy evaluation pillar. Third is technology transition, and this is really focused on, whereas policy was focused on regulatory decision makers, this is mostly focused on private investors, and really recognizing that right now storage has substantial project risk, it has market risk, it has manufacturing risk, and what are some of the tools at DOE's within our quiver, so to speak, that can address that. And some of that is demonstration projects, really going out and collecting a lot of data that can be validated in the field. Some of it is developing new financing finance products. Some of it may be collecting and disseminating market data that's going to allow more corporate investors, for example, to make decisions and to put more money, feel confident putting more money into the sector where it makes sense. And you see at the bottom here, a request for information. We will be coming out with a formal request for information on this strategy, hopefully in the next few weeks. Fourth is manufacturing. Recognizing, as I said before, that there are a number of different elements of manufacturing where DOE has a role to play in promoting and driving U.S. leadership in storage manufacturing. I think part from our administration is interested in learning some lessons from our experience with solar, where we certainly were able to achieve pretty significant performance targets from the Sunshot Initiative, but there was, I think, a wish that some of the manufacturing perhaps had stayed in the U.S. And so that's an element of it, but that's not the only element. A big part is really making sure the U.S. is consistently leading and driving manufacturing innovation. And maybe I think there's a lot of thought that is probably the single biggest way to ensure manufacturing stays in the U.S. is to ensure that we are continuing to innovate in manufacturing. Certainly scaling up manufacturing, of course, but then also looking at supply chain issues and end-of-life issues. It doesn't do a whole lot of good to have the best technology in the world at this point if the supply chain is quite vulnerable, whether it's to deliberate actions or just to the type of scenario that we're all living through right now. And then end of life, I think increasingly for batteries, we recognize as a big issue in recycling. That comes up again and again. We have a recycling prize that's out right now, but continuing to drive research there. And then lastly, on workforce, we know that we know a number of companies in the storage space in particular have gone as far as setting up their own sort of college or technical college curricula because the quality of the workforce doesn't exist right now, and the quality of the speed with which the technology is evolving isn't being kept pace always by lessons. And given though I just see Tom's face popping up and he's a professor, I would like very much to hear your take on this as well. But this recognizing that we have a number of different programs, particularly in the Office of Science, surprisingly, in DOE that do this, that really place graduate students, for example, in national labs. I know my program has just piloted one where we place graduate students in private companies as well. So a lot of different ways in which DOE can play a role in building up the workforce and understanding to what extent and what are really the technical capabilities that we want to focus on for the next generation of engineers. So lastly, we've got a number of different ways that you can engage and get more information. The request for information will come out. That'll be very formal, but we'll also have a series of virtual workshops. We're still finalizing the dates for some of those, but the first one will be May 1st. And then we'll have 3 quasi-regional workshops to the extent a virtual workshop can be regional in May. We can work with ESIG to disseminate those dates when we have them to this group here. And if it's possible, you can all use your own crystal ball. We'll have an in-person workshop on June 26th in Arlington, Virginia. And so with that, I'll turn it back to Tom and to Eric Hsieh, who will talk about the technology development portion.
Thank you very much, Alejandro. So the handoff now goes to Eric Hsieh. Eric is the Director for Grid Systems and Components at the U.S. Department of Energy. His group conducts cutting-edge research and development for new grid hardware technologies, including energy storage, robotics, and power electronics. He previously held positions at Nexam's A123 Systems and the Federal Energy Regulatory Commission. Eric received degrees in public policy from UC Berkeley and computer science from MIT. And he was recently named a Young and Rising Star by Public Utilities Fortnightly. So Eric, take it away.
Great. Thanks, Tom, for including us again. And as Alejandro mentioned, my day job is overseeing the hardware side of the grid R&D portfolio. My night job is creating a unifying R&D framework for everything from sodium-based flow batteries to concrete thermal storage to rocks on rail cars. And so with such a diverse technology set, what we've decided to do is start with what benefits the end user, whether you're a home or town or state or region. And then armed with the functional requirements, any technology can make the case that incremental R&D support can help achieve those goals. And that's what we're trying to do within the technology development pillar of the Energy Storage Grand Challenge, which is, advance the state of the art, or create an environment where these advances can be made very quickly in all aspects of energy storage technologies. So what I'm going to talk about are the 6 use cases, how they hint at what could be possible by 2030, and how DOE can help foster a robust U.S. energy storage industry. So the first of the 6 is facilitating an evolving grid. And this includes the drivers such as aggressive decarbonization goals or transitioning from a world with monotonic load growth everywhere to more pinpoint investments. While values for seasonal storage calculated today are probably 5 to 10 lower than what storage prices are now, it gives us a good target to aim for over the next 10 years. The next case is serving remote communities. And this is one of the use cases where hybrids are going to be key. So storage alone can't fulfill these functions, but it will be a key enabler. So if you look at potential use cases, examples of use cases, remote communities that depend on delivered diesel fuel see very high LCOEs, often 50 cents a dollar or more. And storage coupled with something else could be very useful. One of the other things that I find really interesting are emerging goals, like Oregon's 2-week Ready program, where they're encouraging a significant number of their households to be able to survive on their own for a minimum of 2 weeks. And while 14 days has a different connotation under this world context, this goal was actually established a couple years ago so that Oregonians would be resilient to a major seismic event. And while power generation isn't an explicit part of this requirement, it's useful to think about 2 weeks as the next level of performance achievement for very low-cost energy storage. The third, and probably one of the biggest use cases, is, of course, electrified mobility. And the biggest driver there is going to be the stress on the distribution system for emerging extreme fast charging capabilities. Just as a factoid, the power equivalent of gasoline refueling, so the rate at which gasoline enters your tank, is about 3 megawatts, so 150 miles of range per minute. Extreme fast charging is fast, but not quite that fast, still in the 300 to 400 kilowatt power range, but still having new loads that have very pinpoint and very peaky characteristics are potentially could need some kind of buffer at the interface between the vehicle and the grid. The fourth use case is interdependent network infrastructure. And we call this out because there are other infrastructure sectors that themselves are critical to the operation of the electricity grid. So that includes natural gas, water, telecom, IT, and financial services. And as you see here, a lot of facilities today already have 24 to 72 hours worth of backup. Fuel cells are often a solution. But it's interesting to think if there are other technology pathways that could eventually provide co-benefits, especially when the resilience aspect of it isn't not immediately needed. The fifth use case is critical services resilience. And this includes any sector that is critical to life, health, and safety, including defense, emergency services, government facilities, and public health. The most common solution today is probably the diesel genset. And there are duration requirements for on-site fuel storage derived from NFPA 110. Can range anywhere from 24 hours to 2 weeks for hospitals. But the status quo isn't ideal because fuel can age over time. Emissions regulations can limit your annual runtime to 100 hours. So it's difficult to both maintain, test, and operate these things and stay within all applicable limits. You can see here on the right, there are requirements for different facilities in the 24 to 72 hour range. Now, the last use case, the sixth, facility, flexibility, efficiency, and value enhancement, is actually has two subsets. The first is commercial and residential buildings, and the second is energy-intensive facilities, including generators and industrial power process applications. For both of these use cases, there are market values out there today, as you heard from the earlier presenters, especially for adding flexibility to the existing fleet. But part of our stakeholder process going forward is to draw out what these values might look like in 2030. So now, with these use cases, it's useful to think about how DOE might foster a more robust energy storage industry in the future. So you've got these 6 use cases that in 2030 could result in a market that ranges anywhere from $6 to $20 billion in annual CapEx in the US for stationary storage. Making some reasonable assumptions about firm size, you might have 50 to 60 companies or business units tackling all different portions of this space. To get these companies set up, you might want 1.5 times, again, as many demos just to prove out the technology. And those would be spread across the buckets of technologies that Alejandro went through: bidirectional electricity storage, chemical and thermal, flexible generation, and load. Basically anything that accomplishes the functional requirements of the use cases. And each of these technology pathways is going to have a continuum from foundational science and basic materials research and development, all the way to market access issues, a lot of which we've heard about today for hybrids, and eventually high-value deployments leading to wide bankability. And so, as Alejandro mentioned, this is really a preview for the draft strategy that DOE is expecting to release in the very near future. I encourage you to stay tuned to the Energy Storage Grand Challenge website on the DOE, on energy.gov. We'll be posting additional information about when this draft document is released, how you can provide formal comments, and additional webinars that DOE will be hosting that dives into details on many of these aspects. So with that, I'm done, and thanks, Tom.
Thank you very much, Eric. So we do have some time to take questions. So thanks very much to all the speakers for doing such a good job of staying on time. I'm going to be asking some questions that have shown up in the question and answer boxes we've gone along, and I'll try to make sure we give one question to each of the speakers. So we'll start with Alejandro and Eric. So what level of investment do you foresee on behalf of DOE with regard to addressing the energy storage grand challenge? And do you think some of that will be devoted towards storage directly useful in the hybrid power plants?
So I'll start with the softball question, huh? In terms of the total level of investment, obviously, that is up to Congress. I think there are a number of pieces of legislation, including a big storage component into the Senator Murkowski's legislation that didn't, the big package didn't pass, but I think it was very representative of the type of work that Congress thinks DOE should be doing. Obviously, there wasn't a funding number associated with it, but certain things do take money. I mean, particularly demonstration projects are not cheap, and some of those had some authorized funding levels there. The second question is easier. I think it will absolutely include both standalone storage and hybrid systems. We actually have a subgroup right now of this storage challenge that's focused specifically on hybrid systems and looking at where we can bring together some of the programs across multiple different offices to develop and have a strategy for solar PV or solar hydro PV plants. The one number I can throw out is I think combined across the department or even just in the applied offices last year, I think we had about just under $200 million that we're going towards work that falls within the storage grant challenge, but that's obviously not new money.
Right, and just as a comparison, if you were to compare the U.S. energy storage industry to other industries, pharmaceuticals, semiconductors, those industries tend to spend anywhere from 5 to 15% of annual revenues on R&D. And so that can give you a good guide for what the right level might be bracketed around.
Thank you. Next question, there's been a number of questions related to this from Mark, and Mark has been responding to these, so maybe we can get Mark to answer this. So is there a need for the system operator to have visibility of a hybrid state of charge, or can the system operator just use economic incentives to ensure reliability? Mark, there are other things related to that. Why don't you answer that question and perhaps comment further?
Yeah, one point that I didn't dwell on that's key here is that, obviously in markets, market participants are, basically supposed to offer in at their marginal cost. But you can offer in a mix of energy and ancillary services and allow the market to co-optimize that based on what's most needed, most valuable at that time. Now, implicit in here is that, my point is you can actually control your state of charge implicitly through how you construct that suite of offers, and you would vary that across hours and into real time, based on what you want to be doing and what you've done in the recent past. For example, if you actually want to increase the battery state of charge, you would tend to offer in more regulation and reserves rather than energy, because you're typically not going to be fully deployed all of the time for that whole hour for those types of ancillary services. Therefore, you end up charging your battery in order to keep your headroom for that. So my point is that I think with enough analytics and intelligence that it's possible to actually do this, controlling it through your offers to the market, and that you can do that in a way that is not going to be, market power. Obviously, you can't intentionally create scarcity events, but, offering in at your opportunity cost for a suite of services and allow market co-optimization, I see absolutely nothing wrong with that. So I think that kind of is kind of the piece that's critical here to allow that to happen, where the market operator, if they want to have visibility to the state of charge of the battery, it's fine. But, personally, I don't want the RTO to do anything with it, because, if I'm generating PV as well as having the battery, my battery state of charge is not representing my capability for that hour. Because if I have a high confidence PV forecast, I have more energy, right? So you get into issues like that that are, non-trivial, but I think they should actually be the domain of the owner-operator of the hybrid plant.
Thank you, Mark. Here's a question for Andrew. It was interesting that the lowest value for the hybrid was when it was tightly coupled, but when loosely coupled or independent, you have the greatest value by losing ITC credit. Could you comment on that?
Yeah, no, that's a really good observation. I just want to clarify that what you're seeing there is just the impact that has on the capacity credit, not on the overall value or sort of benefit cost proposition of the full plant. So all we were doing is looking at the implications on the capacity credit and developing a method where you could investigate that. But then what that would do is then enable the utility or a developer to take that trade-off on capacity credit that might happen because of the ITC and compare that to what they might see if they were to do a full cost-benefit analysis, where they would look at the net present value of that and see, if I change my capacity credit, is it worth doing that compared to any implications that might have on the ITC? So this provides a framework for analyzing those questions, but I just want to be careful that we didn't answer that full cost-benefit trade-off.
Thank you. We're at half past the hour, but I think we're going to still go for another 5 minutes or so to continue addressing some of these questions. A question for Brendan. How difficult do you anticipate it will be to form a new reserve sharing group as you suggested, provided FERC allows that to occur?
I think technically it's fairly easy. I think the real challenges are institutional challenges, especially with getting the host utility to accept the resource instead of the payment of its integration charge, and that coupled with that is getting the host utility to explicitly define what the balancing requirements are.
And the next question will be for Will. You conclude that there's a high value from co-locating storage. Do you have an estimate of what greater value could be generated if the storage were optimally located within the system rather than at a generator location?
Yeah, so that is a key question. It's a great question, so thank you for that. It is not one that we can answer right now, so it does tee up our future work. So right now, me and Andrew are developing some analysis that will actually look at this decision of siting and basically compare the value of storage across many different nodes in the United States, the different wholesale electricity markets, and then compare that value to the value when it is constrained to be located at the renewable energy node. And so that will get at this question. We cannot answer it now. I've hypothesized in my presentation that siting constraint is a significant one. And so we look forward to seeing whether the quantitative number is really big. And I think what we've heard is that storage prefers locations where it can sell high during high prices rather than buying low. So we've heard that qualitatively, which suggests that storage would rather be in potentially load-constrained areas rather than near renewable energy assets where prices are typically low. Whether or not that is true, we haven't analyzed it yet. So stay tuned for future LBNL reports to answer that question.
Thank you. Next question for Thomas. Do you expect the benefit to hydro plants from the Hydro Plus storage model is large enough to motivate wide-scale adoption by hydro plant owners?
So in the short term, what we're seeing is that there is growing interest. There are a few examples of hybrids. I mentioned American Electric Power. We've heard from other developers who have, kind of informally said that that's something that they're pursuing. Fortum in Sweden is another example of a currently being commissioned system. I do think that there's a question about how the grid will evolve, on the timescale of a decade or more, and whether or not this is sort of a temporary model or a model that will retain value over time. But I do think that in the near term that it's going to continue to be of interest for a variety of value propositions.
Thank you. The next, we'll probably take two more questions here. So one is basically for, I think, Andrew and Mark. There's been some questions about DC coupled, AC coupled, tightly coupled, loosely coupled. Could you just clarify what exactly you mean by tightly coupled, loosely coupled, and then is there a relationship to DC coupled and AC coupled to this?
Yeah, maybe I can start off with that, and then Mark, if you want to chime in. So our tightly coupled case is one where we both assumed that there was some sort of shared constraint that could be the inverter or the point of interconnection, and you restricted the storage to only be able to charge from the solar. So that was our tightly coupled case. And a DC coupled system could look like that. You could have it where the DC coupled system has that shared constraint because of the DC inverter. And then you could also have it where it only is allowed to charge from the solar. But you could configure, as Mark mentioned, you could configure a DC coupled system to have a bidirectional inverter in which it could also charge from the grid. And so suddenly that DC coupled system would look like our loosely coupled one, where we have shared infrastructure, but you also allow the storage to charge from the grid. So I'd say that they don't necessarily map between sort of what Mark described as hardware constraints or configurations versus ours, which is both hardware and sort of like these limitations that might be imposed by something like the ITC or something like that would restrict whether or not you charge from the grid.
Yeah, well said.
So our last question, I think, is a general question, perhaps for Alejandro or any of you on the panel, but today we focused on hybrids that involve storage. Do you see strong opportunities for other types of hybrids? And are there specific tools that are needed to understand the value of such hybrids? And with
I'm curious to hear other people's responses to this. Honestly, I think part of that depends on the cost of batteries, very frankly. I mean, if they come down enough, then they're so easily, they're clear, they're modular, they're easily insertable, adaptable, that it may not be worth it to try to figure out all the different permutations of other technologies, but we've certainly seen value there, and particularly value in places you wouldn't necessarily expect it, like small hydro and solar with incredibly complementary resource profiles in the East, for example. But part of the value there is reducing your battery costs. So if batteries are cheap enough, maybe that value decreases. But I want to hear other people's responses.
Well, this is Mark. I would just point out that as we've seen in other industries, once you actually combine storage with other technologies and treat that as a subunit of things, you come up with all sorts of innovative ways of doing new services and doing things more efficiently. I don't know why we would expect that to be different in the power sector, that, a hybrid, meaning some combination of resources that now has storage with it and software and programmability, is a source of great innovation. And it's, we've seen in other industries, people come up with very surprising things that have great utility to us, So I don't think we should underestimate the value of innovation.
And I can make a small, more technical point on these other technologies, not just storage. And I think, one thing that we found that I didn't highlight is that there are transmission constraints. Queues are very full. And, we've started to see the wind and solar potentially be co-located for the benefit of, there's a lot of land at a wind farm being underutilized. And then potentially, because wind and solar do have some complementarity in their profiles, solar producing during the day, wind more at night, that they can use or fill up that point of interconnection a little bit stronger. And so there's these other maybe technical limits of the system that will push towards other types of hybridization, not just storage, land and transmission being one, but there could be other things that emerge that make this co-location important to consider.
Well, I think it's about time to wrap up. So I'd like to thank all the panelists for their presentations today, and thank all of you for your participation. On a related note, FERC announced a technical conference on hybrid plants on July 23 and is searching for speakers to self-nominate until May 15th. I'd like to remind you that the next Tucson webinar, Session 10 on challenges with high inverter-based resource penetration, chaired by Julia Matavisian of ERCOT, will be held on Tuesday, April 28th at 3 p.m. Eastern. You can find the full schedule of upcoming sessions on the ESIG website. Thanks again for your participation. Stay safe, and we look forward to seeing you all the next time around.